In Module 2, we examine a number of ways to approximate complicated functions that can be difficult to evaluate directly. We start with linear approximations, the simplest kind, and work up to more precise approximations using Taylor's polynomials. As you might have noticed already, functions can become complicated and they become difficult to evaluate. This was even more the case before desktop computers and programs such as MATLAB became readily available. The methods we examine in this module were developed to provide ways to analyse functions such as finding maximum or minimum points that otherwise would have been very difficult to do. When using an approximation, it's useful to know how precise it is. At the end of this module, we'll examine a method of estimating the error associated with a particular approximation. The simplest approximation is a linear approximation. We'll begin with that. You should be familiar with the equation to the tangent of a function from Lecture 4. The linear approximation is based on this equation. We have a function, f of x, and we want to make an approximation about some point A. This is what we do in all of these approximations. We have a particular point, A, and we make an approximation to the function at points close to A. We start by drawing a tangent to the function at point A. We call that px. And here we have the equation to that tangent px. We can see that for values of x close to a, the value along the tangent px is close to fx. Those are quite close there. In this case, the closer x is to a, the better the approximation. So in the linear approximation, it's the value of this tangential function, px, that we use as an approximate value of f of x. Note that at point x equals a, f of x and p of x have the same value, and they also have the same first derivative. The slope of the tangent is equal to the slope of the function. What we do is to evaluate the function at fa, find the first derivative, evaluate that. That gives us an equation to the tangent, and then we can substitute in values of x close to a that give us an approximate value for f of x. Here are a couple of examples. We'll work through example 6 now. You can watch the video for example 7 later. It's the derivation of a useful rule of thumb often used in finance, the rule of 70. We want to find a linear approximation to the cube root of x for values of x close to 1. In the general form of our linear approximation, we specify a point a rather than a particular value. And so our linear approximation formula is that f of x is approximately equal to the function evaluated at point A plus the first derivative of evaluated A times x minus A. So basically our equation to a tangent. In this problem, A is equal to 1. We want to find f of A and f prime A. First, let's find the first derivative. F of x is equal to x to the minus 1/3. The first derivative is equal to 1/3 x to the minus 2/3. That implies that f1 is equal to the cube root of 1. That's equal to 1. The first derivative evaluated at 1 is equal to 1/3, 1 to the minus 2/3. Well, that's equal to 1/3. Now we can substitute these values into our formula. That's our general form. And so when a equals 1, we have that. We found those values. So the function at 1 was equal to 1 plus f prime evaluated 1 was 1/3 times x minus 1. So we'll have the cube root of x is approximately equal to 1 plus 1/3 x minus 1. This is our linear approximation for the cube root of 1 for values of x close to 1. Now let's use that to find the cube root of a particular number. We'll find the cube root of 1.03. That's approximately equal to, well, it'll be 1 plus 1/3. Where we see an x, we substitute in 1.03. I'm going to subtract 1. It's approximately equal to 1 plus 1/3 times, well, 0.03. And so we find the cube root of 1.03 is approximately 1.01. We can improve on the linear approximation. That is, we can decrease the difference between the actual value of the function at a point and its estimated value. We can replace the linear approximation, the straight line, with a quadratic approximation. We can see how that might work from this diagram. Instead of having a linear tangent, we've got a curve function. The red curve is p of x. This is the general form of the quadratic function. The third term is the concave or convex function that we're familiar with. We can think of these first two terms as being there to move the function around into the right position. Given this general form, the problem now is how do we find values for a, b, and c? As we saw with the linear approximation, at point A, px and fx have the same value, and the first derivative have the same value. The same goes for the second derivative. We have three unknowns, a, b, and c, and we have three equations. Using this information, we can solve for a, b, and c. We take the first derivative of our function p of x. That gives us b plus 2c times x minus a. And then we take the second derivative, so p prime prime of x is equal to 2c. So, substituting into our three equations, this one, and this one, when x equals a, p of x is just equal to a. These two terms are equal to 0. When x equals a, p prime x is just equal to b. And when x equals a, the second derivative is equal to 2c. Just rearranging that last equation gives us that c is equal to 1/2 times the second derivative evaluated at a. Obtaining a, b, and c gives us the formula to the quadratic approximation. This term was a, its first derivative is equal to b, and 1/2 times the second derivative is equal to c. We can see from this diagram how a quadratic approximation can provide a better estimate for a function than a linear approximation. First, we have the linear approximation based on the tangent, and then a quadratic approximation. Let's apply that to the function y equals the cube root of x about the point x equals 1. Remember, we always make these approximations about a particular point. Here we find the quadratic approximation for the function y equals the cube root of x about the point x equals 1. This is our formula for the quadratic approximation. Compared to the formula for the linear approximation, we have an extra term. This is the quadratic term. It's nonlinear, so it gives us a slightly better approximation for fx. We want to find fa, f prime a, and the second derivative evaluated at a. We'll find the first and second derivatives of the function f of x, and then evaluate these three terms at the point a. Y equals f of x is equal to the cube root of x, or x to the 1/3. F prime x, of course, will be 1/3 x to the minus 2/3. The second derivative, f prime prime x, will equal minus 2/9 times x to the minus 5/3. We evaluate these three functions for a equals 1. Function evaluated at 1 is 1 to the 1/3 is equal to 1. The first derivative is equal to 1/3, 1 to the minus 2/3 is equal to 1/3. And the second derivative evaluated at 1 is equal to minus 2/9. 1 to the minus 5/3 is equal to minus 2/9. Now we substitute these three values back into our quadratic formula. Here's our quadratic approximation formula. Let's substitute in those values we just found. Fx is approximately equal to, well, the function evaluated at a was equal to 1, plus the first derivative evaluated at a was 1/3 times x minus, well, a is 1, substituting there, plus the second derivative evaluated at a was minus 2/9 times x minus 1 squared. We can simplify that so that f of x is approximately equal to 1 plus 1/3 x minus 1 minus 209 times x minus 1 squared. This is our quadratic approximation formula for the function y equals the cube root of x around the point x equals 1. That means we can calculate approximate values for the cube root of numbers close to 1. Let's look at the number we estimated in example 6, the cube root of 1.03. Well, that will equal 1 plus 1/3. Where we see an x, we substitute in 1.03. 1.03 minus 1 minus 209 times 1.03 minus 1 squared. We carry out that calculation and we find that the cube root of 1.03 is approximately equal to 1.0099. That's a bit more precise than the value we found in example 6. We saw how we can derive the quadratic approximation. We can use the same method to derive higher order approximations. The general case is the nth degree or nth order polynomial approximation. Px, the polynomial, approximates fx, the function we want the value for. It's an nth degree or nth order polynomial because we have x to the positive powers up to n. The idea here is that each successive term in the polynomial makes a slight adjustment to the approximation that gets it closer and closer to the function we're estimating, fx. Just as we did with the quadratic approximation, we need to find values for the coefficients a0 up to an. The process is the same. We know that px touches fx at point A, so fa is equal to pa. We also know at point A the derivatives of f are equal to the derivatives of p from the first derivative up to the nth derivative. We use these restrictions in solving for our coefficients a0 to an. Let's see how it works for the case where n equals 3. We have px, our third order polynomial. We want values for a0 to a3. We take the first through to the third derivatives of px, and then we let x equal a. For px, when x equals a, these three terms are equal to 0, so px is equal to a0. For the first derivative, when x equals a, these two terms are equal to 0, so the first derivative is equal to a1, and so on for the second and third derivatives. We follow a similar process if n is greater than 3. These equations allow us to solve for a0 to a3, and we plug them into our polynomial. This is the general form of the nth order polynomial. It's called a Taylor's approximation or a Taylor's series. The concept of a Taylor series was formulated not by Taylor, but by the Scottish mathematician James Gregory, but it was formally introduced into mathematics by Brooke Taylor in 1715. In general, the larger is n, the more precise the approximation. But of course, the function we're approximating, fx, has to be differentiable at least n times. For example, we can't have a sixth order polynomial approximation for a function whose highest order is, say, 4. This is just the polynomial in summation notation. The two forms shown here are equivalent. We can apply a third order approximation to the example we had earlier, y equals the cube root of x about x equals 1. This is very similar to the quadratic approximation from example 8. You can pause now and go to example 9. However, we're looking at a different example of a third order approximation shortly, so perhaps you can leave it to the end of this video. A special case of a Taylor series is when a is equal to 0. This is also known as a Maclaurin series. The textbook uses a Maclaurin series in developing the remainder for the Taylor series. Their explanation of why they use a equals 0 is, I think, a little too brief. Here I'll explain the difference between the Maclaurin series and the Taylor series, and then we'll go on to develop the remainder. Since we're letting a equal 0, the Taylor series becomes simpler. If we have x minus 0 to the n, that's simply equal to x to the n. So for a Maclaurin series, wherever we see x minus a, that becomes just x. So we'll have x to the 1, x squared, x cubed, up to x to the n. And the derivatives are evaluated at 0. So Maclaurin series is used for approximations where x is close to 0. Before we go on to see how the textbook uses a Maclaurin series in determining the remainder of a Taylor's polynomial, here's an example of its use in estimating a function. We'll use this example when we find the remainder, so let's go through it now. In example 10, we're finding the third order approximation for the function y equals 1 plus x to the half for values of x around 0. This approximation allows us to calculate the square root of numbers close to 1. For example, 1.05. As I mentioned earlier, where we have an approximation about x equals 0, it's a simplification of the Taylor series, and it's called the Maclaurin series. We can either use the Maclaurin series here, or the more complete form of the Taylor series. Personally, I think it's easier to stick with the Taylor series, no matter what the value of a. Hopefully, you'll see in this case, the two forms are equivalent. We need to find the first, second, and third derivatives and evaluate them for a equals 0. We'll do that. Fx is equal to 1 plus x to the half. We use the chain rule to find f prime x. It's equal to 1 half 1 plus x to the minus 1 half. The second derivative is equal to minus 1 quarter 1 plus x to minus 3 on 2. And the third derivative is equal to 3 on 8 times 1 plus x to the minus 5 on 8. If you're not comfortable with how I obtain those derivatives, you should revise Lecture 4. Next, we want to evaluate the function and the derivatives for a equals 0. F naught is equal to 1 plus 0 to the half. That's equal to 1. F prime naught is equal to 1 half 1 plus 0 to the minus 1 half. So that's equal to 1 half. F prime prime naught is equal to minus 1 quarter 1 plus 0 to the minus 3 on 2. It's equal to minus 1 quarter. And the third derivative evaluated at 0 is equal to 3 on 8 times 1 plus 0 to the minus 5 on 2. And that's equal to 3 on 8. We substitute these values into either of these formulas, this one or this one. As I said, I think it's simpler to use the Taylor approximation in all cases, so I'll use that. Here's our approximation in summation notation. 1 plus x to the half will be approximately equal to 1 plus 1 times a half x minus 0 plus 1 on 2 factorial times minus 1 quarter x minus 0 squared plus 1 on 3 factorial times 3 on 8 times x minus 0 cubed. Simplifying that, we'll have 1 plus x to the half is approximately equal to 1 plus 1 half x minus 1 on 8 x squared plus 1 on 16 x cubed. We want to find the square root of 1.05. To do that, we let x equal 0.05. The square root of 1.05 is approximately equal to, will be 1 plus, well, half 0.05 minus 1/8 0.05 squared plus 1/16 0.05 cubed. And so our approximate value is 1.0246953. An nth order polynomial gives us an approximation for the function f of x. it's natural that we should want to know how good an estimate it is. We have our function. The difference between this function on the left and the polynomial on the right is the remainder, r. If we add r to the polynomial, we get an equality. R is a function of both x and n, but in general we can say as n gets larger, r becomes smaller. Here's a formula for r. The proof for deriving the remainder involves the mean value theorem, which we won't go into in this course. It'll be sufficient to understand how it works. The remainder looks very much like the n plus 1th term in the polynomial. We have x to the n plus 1, we have 1 over n plus 1 factorial, and we're taking the n plus 1th derivative of the function. However, we have this value there as z. Remember, in this case, we're finding an approximation for the function where x is close to 0. Z lies somewhere between 0 and the x we're evaluating the function for. We can't find the exact value for r, but what we can find is the upper limit that we'll take. So that gives an upper limit to the error associated with our approximation. In other words, the error will be at most r. So, how do we put this formula into practice? We consider the interval 0 to x and determine when the absolute value of the n plus 1th derivative, f to the n plus 1 of x, is greatest. This is the value m. If we compare this formula to the remainder, we can see we've replaced f to the n plus 1 of the function evaluated at z there with m. We're also taking the absolute values because when we're considering an error, we're not concerned whether it's positive or negative. We find m by taking the n plus 1th derivative and then determining its largest value between 0 and x. You'll see how that's done in the following example. So we see that finding the maximum error is a matter of deriving the n plus 1th derivative of the function f of x, working out its maximum value over the interval 0 to x, and then plugging that value, m, into the remainder formula. Here's what's called Taylor's formula, which includes the remainder. Although our textbook doesn't show it, we can use the Taylor's formula for approximations for values other than 0. Instead of the x's here, we would have x minus a. We'd also evaluate the function and the derivatives at f of a. It's the same process. The polynomial is just a little bit more complex. However, since our textbook just looks at the special case of a equals 0, we'll stick to it as well. Now let's see how we can use the remainder formula. In example 10, we found the third order approximation to the function y equals the square root of 1 plus x for x around 0. How precise was that approximation? One way of determining the precision is to determine the maximum error associated with that approximation. How do we do that? We look at the remainder term and we find its maximum value. We want to find the remainder for the third order approximation for y equals the square root of 1 plus x around x equals 0, and then find the maximum value of that remainder, and that'll be the maximum error for our approximation. The general form of the remainder is this. Let's go through the terms here. For an nth order approximation, the remainder is n plus 1, so that gives us this coefficient here. It'll be the n plus 1 derivative of the function that we're looking for. And again, we have x to the power n plus 1. This formula gives us the remainder for the approximation for x about 0, in other words, a Maclaurin series. If we had a Taylor approximation around some number other than 0, then we'd replace the x here by x minus a to the n plus 1. However, the textbook just focuses on the Maclaurin series for approximations about x equals 0, so we'll stick with that. The z here is a value of x that we determine, and that's the value of x that maximises that n plus 1th derivative. Let's look at how we determine z and say the maximum error for the third order approximation. For a third order approximation, n is equal to 3, so of course n plus 1 is equal to 4. The remainder then, r4 of x, is equal to 1 on 4 factorial times the fourth derivative of x evaluated at z times x to the 4. For the function 1 plus x to the half, the fourth derivative is equal to minus 15 on 16 times 1 plus x to the power minus 7 on 2. This is the stage where we determine z. We want to find the maximum of the absolute value of the fourth derivative. What determines the size of the fourth derivative? It changes as x changes. This is equal to minus 15 on 16 times, 1 over 1 plus x to the 7 on 2. As x increases, the second term will decrease, so we're dividing by a larger number. I think we can see that the fourth derivative has maximum value when x equals 0, since it gets smaller and smaller as x increases. The maximum value of the fourth derivative then is equal to the absolute value of minus 15 on 16 times 1 plus 0 to the minus 7 on 6. That's equal to 15 on 16. That's equal to m. The maximum error is given by this formula. So we found z, and we're replacing the fourth derivative with a particular value m that maximises the remainder. For our third order approximation, we can substitute in there. We'll have 15 on 16 times 1 over 4 factorial times the absolute value of x to the fourth power. That's equal to 5 on 128 times the absolute value of x to 4. Now we can find the maximum error for the approximation in example 10. We had x equal to 0.05. We substitute in for x. That will be 5 on 128 times 0.05, or the absolute value, to the power 4. And that's equal to, it'll be 0 and 6 more zeros, 2441. Or in more succinct notation, 2.441 by 10 to the minus 7. That's the maximum error, so our third order approximation was quite precise.